The entire sequence program of this example is generated in a function block for which we select the language graph in the Semantic Manager. The S7 graph editor is started automatically by opening this block. First, we provide you with some characteristic elements of the S7 graph editor. The toolbars contain symbols on which you can click to access the most frequently used menu commands. The work area is a window within S7 Graph in which one or several sequence chains can be displayed and processed. The sequence chains represent the program code. The Overview window contains 3 tabs whose contents help you with the orientation and processing of large sequence chains. The Details window at the bottom of the screen, with its various displays, supports you in generating the program. Processing a sequence chain always starts with a so-called initial step. The current step remains active until the switching condition or transition, which may be made up of ladder or FBD elements, is true. Then the next sequence step is processed. In addition to the program, extensive comments are possible in the comment field as well as in every step directly. Let us now take a closer look at the program for our example. Let us consider the scene in which the workpiece is moved under the drill. The name of the sensors and actuators, here referred to as I and O, were filled in the symbol table of step 7 beforehand and are now used in our S7 graph program. We start programming the sequence chain with the initial step S1, followed by the transition T1. As a first action, the workpiece is to be moved under the drill. To start this action, we created the following AND logic operation as transition T1. The magazine is to be filled with workpieces and the slider is in the starting position. A start signal, for example from a switch, activates the slider. If transition T1 is true, step S1 becomes inactive and step 2 active. There we set variable O1 for starting the slider, which causes it to slide the workpiece under the drill. If the slider reaches its end position with I2 equals true, it is stopped in the now active step S3. Let us now take a look at the drilling process as the next work step. Here we will meet a simultaneous branch at which both chain parts are processed as it were in parallel. Sensors I3 and I4 indicate the end positions of the cutter block. This information is used as transitions in order to have the drill execute the vertical movement in steps S4 and S5. During the entire drilling process, compressed air for chip removal is to be applied to the workpiece. From the toolbars, we therefore insert a simultaneous branch in order to activate the compressed air parallel to the drilling process. Our sequence chain is terminated with the last process step, ejecting the workpiece. When the drill is back in the starting position, the slider also moves back to its original position. As soon as this has been reported by sensor I1, the ejector starts and ejects the workpiece before being pulled back to its original position by a spring. As soon as the slider reaches its basic position, the last transition T9 of the sequence chain becomes true. Basically, the sequence chain can now be terminated or a further sequence chain be started. In our example, the chain is processed cyclically, meaning another work operation starts in the first step S1 of the sequence chain. So far, we always assumed that the magazine was filled with workpieces. We now want to poll this status in the sequence program and react so that no action is to be started if the magazine is empty. This task requires a branch part to be processed as an alternative to the main chain. For the realization, S7 graph provides us with the alternative branch. At the transitions T1 and T10, we check the sensor which monitors the magazine. If no workpieces are left in the magazine, transition T10 is true and an indicator light is switched on. Transition T11 ensures that step S1 of the sequence chain cannot be jumped to until there are workpieces in the magazine. A comparison between the sequence chain in S7 graph and the technological sequence structure shows that their structures are equal. In the latter case, we can easily generate a runnable PLC program using S7 graph. S7 graph provides further support by means of functions not shown in our example, such as counter, times, arithmetics, jump commands, or also the option of calling other blocks, so that S7 graph is also especially suitable for complex applications. How is the complete S7 graph program integrated into the existing S7 project? After saving the sequence chain, a runnable function block is available in the block container of the Semantic Manager. For it to be applied within the S7 project, it must be called, for example, in the cyclically processed organization block OB1. When parameterizing the block, you can select which of the 4 possible operating modes the sequence chain should work in. For testing or commissioning, we then load the S7 project into the S7 CPU, including the now integrated S7 graph function block. You can now monitor the sequence chain online as well as in the work area by triggering the monitoring function in the overview window. Additionally, S7 graph offers further functions for effective process monitoring and control. The step monitoring, the so-called supervision, enables you to monitor execution times of actions, for example. In case of an error, the step remains active. However, it is not switched to the next step. The event can also be easily generated as event message or alarm message. This also applies to the so-called interlock, in which you can define locking conditions for each step. Here, all actions to be executed are only activated if the interlock conditions are true. For all automation tasks with sequential structures, S7 graph is the optimal engineering tool. Use the benefits of this graphic programming language in order to easily realize the requirements of your automation task successfully in a time and cost-efficient manner.